Right, we'll move on to our next presenter, Daniel O'Connor, and he's going to be from UCL, and he's going to be covering quantum annealing for network optimization. So, Daniel, over to you.
Brilliant. Thank you, Mike. So today I'm going to talk about what I'm researching in my PhD, and that primarily concerns quantum annealing for network optimization. So some of the hardest problems in computer science are concerned with discrete optimization. For example, we have the traveling salesman problem on the left here, where we have a set of points and we want to find the shortest path that visits all of the points. And this problem normally has a cost function associated with it, and here the cost is obviously distance, and we get some landscape as we can see here on the right. So, and our best possible route we can take is the minimum or the global minimum indicated by the star there. But typically, modern day algorithms tend to find something close, a local minima, that's not quite optimal, but is still good enough approximation nonetheless. But obviously, if we can use another method that can find the optimal, we can find a better solution, as you can see here on the right. And to be able to get to that better solution, we need to be able to traverse this landscape and maybe jump over the barrier. Maybe some of you are familiar with simulated annealing, where we use thermal activation to traverse this landscape and get to better solutions. But in quantum annealing, what we use is something called, we use quantum tunneling to traverse the landscape instead. And how this protocol basically works is that we start from a simple quantum state, which you can see there on the left of a very easy to determine space. And what we do is we anneal from the quantum state to the classical system, and therefore we should end up in the ground state of the system at the end of the anneal. What this actually looks like in real life is a bunch of quantum spins, or qubits for short, which are in a superposition of all possible classical states. And because they can see every possible classical state, and when we slowly anneal, we should end up in the ground state at the end of the anneal as well. The current state of the art is run by a company called D-Wave Systems. They have over 5,600 quantum spins or qubits in their quantum processing units. And an example is shown on the left here with their Pegasus architecture with only 264 qubits, so you can imagine what 5,600 looks like. And using hybrid methods such as classical optimization methods like to-do searches, with quantum annealing, you can solve problems of up to 1 million variables, which is quite an impressive amount. So why quantum annealing in general? You get more qubits than any other noisy intermediate quantum system. D-Wave annealers only consume 25 kilowatts, which is obviously interesting considering Frank's talk earlier, which it's a lot lower than, say, these data centers and supercomputers, which consume on the order of megawatts. And it's also can be applied to a range of problems in optimization, machine learning, and materials science. And with networks specifically, it's been applied to job scheduling problems and also large-scale MIMO processing as well. The con to this is that it's not a universal form of computation, such as a universal quantum computer using gate-based methods. There is an undetermined speed up, and there's hardware constraints because qubits can only see so many other nearby qubits. So what we do at UCL is that we look at to explore the physics of quantum annealers. We have our own qubits, which we run experiments on. But what I'm primarily concerned with is obviously more of the theoretical side of things and experimenting with the D-Wave as well. So what we've done, as an example of what we've been doing in our work here, is we've got a cost landscape here where we've got the same barrier heights, and our local minima on the left and right have different distances to our ground states. So we can thermally activate the same from each direction, but it should be harder to get from one well to the other well in this landscape using quantum tunneling. And how we can do this is that we can start on these local minima by using something called reverse annealing, where we start in a predefined initial states. And what we do is we induce some quantum fluctuations by some amount, which can induce tunneling, and such that we can reach the ground state again, which is kind of attributed to a kind of a local search mechanism. And so what we can do is that we can start in these wells, we can see on the left, and we can run this on the D-Wave. And what we can see is that as we get different results. So what we've got on our results on the right there, along the y-axis, we've got probability of reaching this ground state against the magnitude of quantum fluctuations induced into this kind of problem that we're applying. And we can see that basically the closer you are to the ground state, the higher probability you have, and it's ordered consecutively as well, which is very nice. The mechanism behind this is still being explored, but it's something that's of great interest to us. So in summary, quantum annealing can be used to solve discrete optimization problems, and it's readily been applied to network problems such as MIMO processing, and there's ongoing work for a provable quantum speedup.